Welcome back, everybody. So going over question 51. Don't worry about 52 there. Send to a new page. The graph of a function f is shown. Which graph is the antiderivative of f? So we're looking at this one here. This is our original function, f. So basically, f is the derivative, right? Hold on there. What's the four numbers? 4935. So f is the derivative. Now, if the derivative is below the x-axis, what is that telling me about the original function? It decreases. From this point to this point, it's got to be decreasing, right? Because it's below the derivative is below the x-axis. Well, which is the only one of these? Look, a increases, c increases. So the only function that this could plausibly be is c. That's the only piece I really even need to think about. The rest of the function makes sense too, because like here, at this point, that's when it needs to start to increase. Doesn't this point look like the minimum value of b? Yeah, and then it can start to increase as well. All right, what are the questions on the homework? Yes? You did not have to do that one. Nope. I thought I took, did you mean 61? Okay, yeah, 61. You did not have to do 69. Sure. 28. All right, finding the antiderivative. What are we doing here? Find f. Yeah, here's f double prime, find f. Guys, remember what I said yesterday. If you can possibly turn it into just a variable with an exponent, that's going to be best. Like for this one, since this is, since f double prime of x is 1 over x squared, I'm going to rewrite that as, whoa, not 1 over, but just x to the negative second. Because that's going to help me out. All right, so that means f prime of x is going to be, okay, kick up the power, x to the negative 1, divide by the power. So negative x to the negative 1 power. Make sure I'm doing this. Yeah. Plus c. And then to get to f, well, remember that this, I could have rewritten this as negative 1 over x, right? Plus c. Remember that that's a special one. 1 over x is special. It's got to be ln. Negative out front means negative ln of absolute value of x. Remember, got to keep it positive because ln can't, you can't evaluate negative of a log. Plus cx plus another constant, d. And we can stop there. Does that make sense? Any other questions on the homework? Okay. Well, then let's get into the notes for section 5.1. Section 5.1, area and distances. Area and distances. Again, chapter 5 is all about I believe the title of chapter 5, let me look at it. I believe it's integrals or integration. Yeah, integrals. Again, we're going to use antiderivatives to find integrals. Okay? We're going to use antiderivatives to find integrals. Now, to understand what an integral is, we need to start by doing this area problem, okay? Actually, this is all about area, not even any distances. I don't know why they call it area and distances. In this section, we will discover that in trying to find the area under a curve, or actually, okay, distance traveled by a car. Okay, we get that. We end up with the same special type of limit. Either the area and the distances, distance traveled by a car, we end up with the exact same special type of limit. It's actually the limit of a sum. The limit of a sum. We're going to be using some summation notation. You know that big sigma, the big E looking thing? You guys used that last year in pre-calc? Yeah, like this looking thing. The summation notation. We're going to be using that in this section a lot. All right. Now, let's first start thinking about generally what area is, right? Area is like the amount of space something takes up. And in general, we could use formulas that we have for area, but if it's an irregular shape, we don't really have a formula for it. Like, for example, if we've got, a rectangle, we could just plainly do length times width, right? If we could do a triangle, we could do 1/2 base times height. But if we've got something weird like this, then what we could do is possibly break it up into pieces that we can find the area of, and then add them back together, right? That's one way of finding the area, right? We can break it up into simple shapes that we use, that we can find the area of using formulas that we know, and then add them back together to find the total area that we have. So what we're going to do here is, in this section, find areas of things like this, okay? So what we're going to be given is we're going to be given curves. And then I'm going to ask you, okay, find the area underneath that curve, which is in essence an integral. Find the area underneath that curve from some point to some other point, from A to B. That's what we're going to be doing in this section. Find the area underneath the curve given a starting point and an ending point. But the top is irregular. See, the bottom is bounded by the x-axis, but the top is irregular. The top is some sort of curved shape. So what we're going to do is try to figure out a way so that we can estimate what that value actually is. Okay? Let me jump up back here, see if I wanted to say anything else about that. Trying to solve the area problem, we ask ourselves, what is the meaning of area? Question is easier to answer for regions with straight sides like we show. Area of a polygon is found by dividing it into triangles, or if it's a curved shape, we're going to divide it into things like this. So let's take a look here. Use rectangles to estimate the area under the parabola y is equal to x squared from 0 to 1. This is a very common method. The book just calls it use rectangles to find the area of. I've seen it as the rectangular approximation method, or abbreviated RAM. Find the rectangle approximation method of the area, or RAM. Okay. So what we're going to do here is we're going to divide up this area underneath this curve into rectangles. Okay. And how many rectangles we have? Well, we're going to see that the more rectangles that we create, the better approximation that we're going to get. So let's first start off by trying to divide this up into certain shapes that we know. Like, for example, I know that if I draw this square in here, now you don't have to do this along with me. I'm just going to go on this path here for a second. If I say this big rectangle here, and it's a square, if I say this big rectangle there, what's the area of that? 1 square unit, right? Okay. Is that an overestimation? A very big overestimation, right? So I know that the area of this is somewhere between 0 and 1, right? What we're going to do is figure out a lower boundary and an upper boundary. Right now, I know it's between 0 and 1. Well, what if I know triangles. What if I make this right triangle in here? What's the area of that? 1/2. Yeah, I stopped it there. 1/2. 1/2 base times height, but base and height are both 1. So 1/2, 1 times 1 just gets us back to 1/2. So I know that the area is now not just between 0 and 1, it's between 0 and 1/2, because isn't this still an overestimation? Right? There's still a piece in there that I really don't want the area of. Okay? So what we're going to do is keep breaking this up into shapes. Well, it says to use rectangles, and I do what I'm told. So let's use rectangles. Okay. What I'm first going to start off with is how do I put this? I'm going to break this up into 4 different pieces. Okay. This is 1/2. This is 1/4. And this is breaking up into fourths. So 1/4, 2/4, 3/4. And this would be 4/4. 1. Okay. What I'm going to do is create rectangles in there. I'm going to create a rectangle here. I'm going to create a rectangle here. And I'm going to create a rectangle here. How many rectangles did I create? 3. How did I know to divide it up into 4 pieces? I just made that up for right now. And that's just showing you how to do this. There are going to be a lot of times where I tell you how many pieces to break it up into. So I'm breaking it up into these 4 shapes. Now, this is called, sometimes it's called LRAM, L rectangle approximation. We're going to have an RRAM, a right rectangular approximation. Why is this called an LRAM? And we're going to denote this by using the letter L. Well, because you see how this point on the curve is on the left side of this rectangle? This point on this curve is on the left side of this rectangle. This is on the left side of this rectangle. Okay? The R is going to be when we put it on the right side of that rectangle. Now, let's figure out what the shapes here are. Well, I've got a rectangle, a rectangle, and a rectangle. What's the base of each of these rectangles? Like, what's the base of this rectangle in there? 1/4. So it's going to be 1/4 times, well, what's the height of that rectangle? Well, it's this distance in here. What is that? That's the y value, right? This is x comma y. That's the y value when I plug in 1/4. Well, what's the equation? X squared. So it's 1/4 squared. Right? That's this little rectangle in here. Let's take a look at the next rectangle. I'm going to add, because again, area is the sum of all of the little pieces of the area. Again, this base in here is 1/4. So I'm going to say 1/4 times its height. Now, the height of this rectangle here is going to be when I plug in, it's the x comma y, 1/2 comma y, right? So 1/2 comma, well, oh, that's yellow. 1/2 squared. Move this over a little bit so I have a little bit more room. And then my last rectangle, again, what's the base of this rectangle? 1/4 times the y value here. When I plug in 3/4, 3/4 comma something, right? 3/4 comma 3/4 squared. So let's run the numbers. Let's see where it comes out. Okay, we've got 0.25 times 0.25 squared. Okay, I use parentheses, sure. And then we got plus 0.25 times 0.5 squared. Why did I keep using parentheses? Plus 0.25 times 3/4, 0.75 squared. Forgive me for using decimals. I really don't want to plug in fractions. 2.21875. Now, is that an underestimate or overestimate? That's an underestimate, right? Because there are pieces that I have not taken into account for. Like I haven't taken into account that chunk. I haven't taken into account this chunk here or here. So there's a lot of area missing within that estimate, right? So that is an underestimate. So now I can say, my upper boundary with that triangle was 0.5. So I now can restrict the area between 0.21875 to 0.5, overestimate to underestimate, right? Okay, so this is the L, the left approximation. Let's do that exact. My Siri went off. Like it recorded everything I just said. Let's do the opposite of this. So here's what I'm going to say. I'm going to repeat this process. Clone. I'm going to move that down a little bit. And I'm going to repeat this process with the right approximation. The right side, not the correct side, but the right side approximation. What does that mean? That means I am going to do that same thing where I cut this up into 4 pieces. This is 1/2. This is 1/4. This is 3/4. Okay. I'm going to do that same thing, but now instead of making this on the left side, I'm going to make it on the right side. What does that mean now? I have this rectangle in here. I have this rectangle in here. I have this rectangle in here. And I have this rectangle in here. Now, in the end, is this going to give me an overestimate or underestimate? It's an over, right? So see what I'm doing here? I'm finding an underestimate, overestimate, underestimate, overestimate to try to get it into some sort of box, right? To try to keep it, try to find some sort of boundary with it. So let's do that same area. So I'm going to do right side approximation. Well, the right side approximation would be this. And again, why is it called right side? Because look at all the rectangles. Do you notice the points along the curve are the right, top right of the rectangle? Okay, so let's keep it going here. Now, again, what are all the bases of these rectangles? 1/4, right? So 1/4 times something plus 1/4 times something plus 1/4 times something plus 1/4 times something, and I kind of ran out of room over there. Because those are all my bases. Okay, base times height. Well, where's this going to be? This is 1/4 squared. This is 1/2 squared. This is 3/4 squared. And this is 1 squared. Oh, don't do that. I just want this. There we go. Just a little bit. Do you know where I got the 1/4 squared, 1/2 squared, 3/4 squared? Because those are all the y value. The y value here would be x comma y, 1/2 comma 1/2 squared, 3/4 comma 3/4 squared, 1 comma 1 squared. Okay. All right, so let's figure out the right side approximation of this. Okay, that gives me 0.25 times 0.25 squared. Again, why am I using a parentheses? Plus 0.25 times, do I even need to do this calculation? Look at all this. That's the first term, that's the second term, that's the third term, plus 0.25 times 1 squared, or just 1, right? So the right side approximation is 0.46875. Yep, good. 0.46875. So I know the area, because that's an overestimate. I know the area is somewhere in between these two values. The true area of this thing is somewhere in between. I shouldn't say we're equal to. It's definitely not equal to. Is somewhere in between 0.21875 and 0.46875. Somewhere in the middle there. Now, there is a left side approximation. There is a right side approximation. There is also a middle point approximation. Okay, because what would happen if I did this exact same process? Clone. I have to sound like a robot when I say clone. What would happen if I did this exact same process with the exact same intervals? So 1/2, 1/4, 3/4, but instead of using a right side, instead of using a left side, I take intermediate values here, 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 and here, and said, okay, I'm going to run those coordinates, and I'm going to take the rectangles at those spots. Because take a look at that. It's giving me some over and some under. Now, do I know exactly if this is an overestimate or an underestimate? No, because I've got some of each. So this is an estimate. I don't know whether it's over or under. Yeah.
So do we have to do the right and left side estimates? Can we just do the middle point?
Okay, it all depends on the type of function that I'm asking you to do. Because if this is odd because it only is going up. If it goes up and down and up and down, it might be better to use right side. It might be better to use left side. It might be better to use middle, but it all depends on the type of function.
So we don't always have to do all three.
Right. Some of them, like a couple of the homework problems says use right side, use left side. Use right side, use left side. Use right side. I'll be specific in what I ask you to do. Yeah.
So if it said like just use right and left side, would you just put that down?
Yeah, you just do these two things. Use right side approximation, use left side
Do
approximation.
you want it written like that then? Or is it not that?
It doesn't really matter. I mean, you can if you want to know that, yeah, indeed the area is somewhere in between there. But if I ask that, like on a homework, I would just want those two numbers.
Okay.
And that's it. Then you're good.
And left side won't always be the underestimate, right?
Correct. Yeah, and that's a good point that she brings up. Left side won't always be an underestimate, and right side won't always be an overestimate. It all depends on the type of the function, okay? The type of function that you're looking at. Because maybe the right side is the under and the left side is the under based on how the rectangles work themselves out. So let's finish off this middle. Let's finish off this middle approximation. Now, how do I figure out where that is? Well, the middle approximation is going to be usually denoted by an M. Okay, where is halfway between 1/4 and 0? 1/8, right? Now, is the bottom of my rectangle still the same? Is my base of the rectangle still 1/4? Yeah. So my base is still 1/4, but now it's times the height of this rectangle is 1/8 squared. Halfway between 0 and 1/4. Okay, the next rectangle, the base is still 1/4, but now this intermediate point in here is halfway between 1/4 and 1/2. What is that? 3/8. And then here, 1/2, this would be a 5/8. And in here, 7/8. Okay, now I'm going to have to use parentheses here because I don't know those decimals offhand. 0.25 times 1/8 squared plus 0.25 times 3/8 squared plus 0.25 times 5/8 squared plus 0.25 times 7/8 squared. 0.3281. 0.3281. Yep. Good. Middle is 0.3281. Do I know whether that's an under or an over? No. That's the problem with middle approximation. You could do left side boundary, right side boundary, but middle approximation, you can't really tell whether, we know it's somewhere in the middle of these things, and we know it's somewhat of a good estimate, but we don't know if it's an underestimate or an overestimate. That's the problem with middle approximation. Okay? Now, I chose to break this up by 1/4, right? Well, Could I have done more approximations? Yeah. Like in a second, we'll talk about, well, I guess why not? Let's jump to this slide. I'll hit example 2 in a second. But what if I had done more rectangles? What if I had done a lot more rectangles? Look, this is the same approximation using 10 intervals, 30 intervals, 50 intervals. And that's right side approximation. Usually the subscript on R, look at that notation, the subscript on R is how many intervals you're using. That's the right side approximation. Take a look at the left side approximation. Same thing using 10 intervals, 30 intervals, 50 intervals. Now, left side approximation, is that still an underestimate? Yes. Is the right side approximation still an overestimate? Yes. But what we're doing here is, I think if you kind of see where we're headed, if I just make that a non-concrete number, if I just make that an arbitrary number, if I just let n go to infinity, it will eventually reach the area underneath the curve, the exact area underneath the curve. If I let n go to infinity, I know that that will eventually lead me to the area underneath the curve, both right side and left side approximation, right? One's coming from the top end, one's coming from the bottom end, and it will eventually lead me to the exact amount, okay? That's where we're headed within this chapter, okay? Now, for the region S in example 1, show that the sum of the areas of upper approximating rectangles approaches 1/3. So I'm going to show here, I'm going to algebraically prove that the limit is actually 1/3. And the limit is actually 1/3. All right. Now, I was using 1/4, right? So that means that every time I had my base, it was 1/4, right? So if I choose to use n, every time I'm multiplying with my base, it's going to be, the area is going to be, oh, that's 3. The area is going to be 1/n times that thing squared, right? So it was 1/n squared. And then I'm going to do that same thing with 1/n times 2/n squared plus 1/n times 3/n squared. Where am I getting that? Well, look back here. What were these numbers? These numbers were, am I doing right side? I'm doing right side. What were these numbers? This is 1/4, this is 2/4, this is 3/4, this is 4/4, right? I'm just increasing that value here, 1/4, 2/4, 3/4, 4/4, right? I'm increasing the numerator by 1 each time. So if I make that arbitrary, I'm going to say that's going to go from 1/n times 1/n squared, 2/n squared, 3/n squared, all the way up to, if I let it go infinity, plus 1/n times n/n squared. And this is just an infinite sequence, right? This is an infinite sum. Now, do you notice here what I see in every single one of my sums, or my products, excuse me? I see a 1/n. So isn't that like the same thing as saying 1/n times the whole sum? 1/n squared plus 2/n squared plus 3/n squared plus n/n. Sorry, I put that in parentheses. Squared. Can't I factor that out? Now, if I evaluate the squared, right? Take a look here. I can do this. I can do the same type of thing here. 1/n times, look, this is 1 squared over n squared plus 2 squared over n squared plus 3 squared over n squared plus n squared over n squared. What do you notice about all of those denominators? They are all n squared, right? So can't I even rewrite it this way? 1/n times 1/n squared
1 squared plus 2 squared plus 3 squared plus n squared.
You see what I did there? I removed 1 over n squared. All right, I'm just going to multiply those on the outside. 1 over n to the third. 1 squared plus 2 squared plus 3 squared plus n squared. Now, this is a special type of sequence. Perfect squares going up to n squared. I wasn't even going to do this problem because this is kind of a very abstract idea. And because you have to know that infinite sequence will actually equal, like this is just a standard thing. I remembered this from, because I took a lot of math classes in college. This is n times n plus 1 times n plus 2. Oh, no, sorry, that's not right. 2n plus 1, I wrote that wrong. All over 6. Okay.
Is that a 1 over n squared? Whatever.
It's a That's just a formula that, like Pythagorean theorem, just sticks out in the brain. This is one of those that sticks out in my brain. See, remember I like those number theory classes? This is one of those things that you prove in number theory. That 1 squared all the way up to n squared, that infinite sequence actually does equal that. You prove it by induction too, it's pretty cool. All right, now, let's keep going with this. Okay. Do you see how I have an n to the third and an n here? What I'm going to do is cancel that n to the third and cancel that n. So we're left with a 1 over n squared times n plus 1, 2n plus 1, all over 6. I'll multiply that n squared in so that I have an n plus 1 times 2n plus 1 all over 6n squared. Now, we're going to do a little funky algebra here. If it wasn't funky enough. I'm going to take the 1/6 out. Okay. You see that's a 1 over 6. I'm going to take a 1/6 out. And then I'm going to kind of break up this fraction. If I remove the 1/6 out of the way, I kind of get it out in front. I'll erase it away so we can see it a little bit better here. What I'm going to do is break up this n squared into n times n. And then give each part of the numerator an n. N plus 1 over n, 2n plus 1 over n. And now if it's a sum on the inside, I'm going to break that up even more. That's 1/6 times n over n plus 1 over n times 2n over n plus 1 over n. Now you may be thinking to yourself, what are we trying to do here? Well, watch what's going to happen. That n over n is going to turn into a 1. The 2n over n is going to turn into a 2. And now, what was n going toward? Well, n was going up to infinity, right? Oh, it's Mrs. Kalala. Hold on a second. Hi, Mrs. Kalala. How you doing today? Yes. No problem. Bye-bye. Let me indicate it to the main office. Sure. Yeah. Or maybe at the, oh, at the end of here, yeah. She said just for a few moments, so. All right, so let's finish this off here. N was going to, the limit n was going up to infinity, right? This is the limit as n goes up to infinity. What's going to happen if n goes to infinity here and here? It's going to go to 0, right? So the limit as that goes to infinity is going to be 1/6, 1, 2. What's 1/6 times 1 times 2? 2/6 or 1/3. So we just proved algebraically that the limit is actually 1/3. I think that's pretty cool. See, it's funny that we talked about me liking number theory, because that's really like a number theory problem, like an algebraic proof. Yeah, I think that's pretty cool.
I thought that was the original question.
Yeah. Prove that it's 1/3. I won't make you do that.
Okay.
I will honestly tell you right now, the first several problems, you probably already know how to do, because we've done it here on the first slide. Okay? So you can do a lot of the first couple homework problems, because a lot of them are just rectangle approximation. I tell you to do left side, I tell you the right side, I ask you whether it's underestimate, overestimate, so on. Caleb.
So what made that question like specific to that graph?
Because I knew that it was y is equal to x squared, this is x squared.
So everything else would be the same except for.
Right. If I were to show any other type of function, like square root of x, I would have to do this exact same process, but in here, these would all be square root of those things. The square root of 1 over n, the square root of 2 over n, the square root of 3 over n. And then it would become a lot more difficult. All right, let me turn off the video here.